All right, let's talk about forces between charges. We know that when I have two masses, m1 and m2, and they're separated in space, and there's some distance between them, which we call r. We call that distance r because it doesn't matter where that mass is. The other mass 1 could be over here, it could be over here. As long as it is a distance r away, like the radius of a circle, as long as it is that distance away, the force will be the same. And we know that this gravitational force of attraction between them is given by the following equation. Well, it turns out if I have two charges, there is a force between those two charges, and that force is given by a very, very, very similar equation. We call this force the electrostatic force, and the electrostatic force is given by the following equation. It should look really familiar. They both have this inverse squared relationship for the distance between them. They both have some constant in front of them. Actually, let me write this constant over here. Okay. And instead of two masses, we're dealing with two charges. That's it. By the way, it turns out this force tends to be a lot stronger than this force. And that's why we can take things like the balloon, stick it to the wall, and it doesn't, fall, or we can levitate things by putting a positive charge and a positive charge and having them hover above. So it turns out that this force is a larger force, which every once in a while they say, compared to the blank force is larger, smaller, whatever. Electrostatic forces tend to be stronger than gravitational forces. So how do we use this equation? And what is K? Well, as you might imagine, I'm going to tell you, K is a value off of your reference table. So let's bring up the Regents reference table. And, oh, I didn't put it on the right mode, so I can't show you my screen, but that's okay. I will just write it down for you. If you go to your reference table, you will find something that says electrostatic constant. Okay. With a value of 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, so now let's look at why these units are the way they are. Well, I want to know the force between an object, and I know it's given by K Q1 Q2 over R squared. If I were to look at this, I don't know what K is right now, but I know that force is in newtons. I know that Q1 is a charge in coulombs, Q2 is a charge in coulombs, and R is a distance in meters. So I need this to come out to just newtons. If I rearrange this, I actually find that Newton meters squared per Coulomb squared is K, and those are the units of K. Because if I multiply meter squared times meter squared, they cancel. Coulomb squared times Coulomb squared, they cancel, and I will be left with just newtons. So how do I use this equation? And how do I deal with positives and negatives? The first thing I'm going to tell you is you're smart. If I have a positive charge and a negative charge, you tell me if they're going to attract or repel. Don't worry about, oh, I got a negative number for the force, I got a positive value for the force. Who cares? Worry only about the magnitude of the force, and then afterwards you can tell yourself, should they be attracting or should they be repelling? Okay? So let's say I have a positive 3 Coulomb and a negative 2 Coulomb charge, and they say, well, what is the electrostatic force between those things? This is a plug and chug problem. It should be very, very simple. All I do is I plug in that the force is KQ1 Q2 over R squared, and obviously they have to give me some distance. Maybe the distance is 2 meters. These are all very simple numbers that you're probably not going to get this simple of numbers on any question. All right, so now I just plug in 8.99 times 10 to the, was it 9th, 8th? I don't remember anymore. To the reference table, 9th. Newton meter squared per Coulomb squared times 3 coulombs times negative 2 coulombs all over 2 meters squared. Very, very important that we put our parentheses and everything, or our calculator might not give us the right answer. And so if I plug this on my calculator, I get negative, oh, you can't see down there. I get negative 1.3485 times 10 to the 10 newtons. Okay, now what does that negative mean? Well, should we be attracting or should we be repelling right now? If you remember, we had a positive charge and a negative charge, so we should be attracting. So if I get a negative force here, means I'm attracting. Do I need to memorize that? Absolutely not. But let's just, common sense this equation. Whoa. The distance between two objects will always be positive. That will always be positive. K, our constant, will always be positive. What about Q1 and Q2? Those are the only things that can switch. If they're both positive, the whole thing's positive. Two positive charges will repel each other. Okay. If I put two negatives in, two negative charges will repel each other, and a negative times a negative isn't get a positive. So if I get a positive answer, I know they're repelling, and if I get a negative answer, it means they have an opposite, and it means they will attract. Do you have to memorize that? No, and the reason you don't have to memorize it is you are smart enough to look at positives and negatives and know what they should be doing. Now, the only other thing I want to say about this is you might get very small distances, and you might get very small, well, not really very small charges, but small charges. I told you that 1 Coulomb was a lot of electrons. In fact, 1 Coulomb is 6.25 times 10 to the 18 elementary charges. That's a lot. And sometimes we don't deal with a whole Coulomb. Sometimes we don't deal with a whole Coulomb. We deal with a little bit less than a Coulomb, I think. I guess I should leave something on here for it to focus. Okay. Come on. You can do it. There we go. We often deal with microcoulombs. If you go to your reference table, you will see that micro means 10 to the minus 6. So instead of giving you, a 3 Coulomb charge, you might get a 3 microcoulomb charge. Before you can do anything with it, for instance, plug it into this equation. You have to change that micro. To change that micro, you literally just write this in front of it. So 3 microcoulombs becomes 3 times 10 to the minus 6 coulombs. And now that is the number you can plug in for Q. I'm not going to go through rearranging this equation to solving for distance, solving for Q, solving for K. That's something we should be able to do. If someone has a specific question about it, I will make a video about it.